All right, so in this example, guys, again, we're just going to use our idea of understanding the parent graph. Before we can do this, though, we recognize we have negative x. Let's write this in a better form. So we have this negative cosecant. That's a negative x plus pi. And we know that if we want to identify the transformations, right, like I gave in the notes, we're going to want to make sure we factor out that b. So we're going to write this as y equals negative cosecant negative x minus pi. That tells me I'm reflecting in the inside, right? So let's go through our transformations. So when we multiply by negative on the outside, that is a reflection about the x-axis. If I multiply by negative on the inside, that is a reflection about the y-axis. So I am reflecting about the x and the y-axis. That means that has a that means you are really reflecting about the origin. And since cosecant is odd, that gives us back the original equation, right? So it really makes no impact at all. But it obviously makes impact as far as our understanding of the graph. But again, I just want to make sure you guys understand, like, this is an odd function. It's symmetrical about the origin. So reflecting about the x and the y-axis actually doesn't change the shape or look of the graph at all. But we need to understand that factoring, because a lot of students will say, oh, yeah, you're shifting left pi. No, no, you're shifting pi units to the right. So we do have a phase shift here. We're going to be shifting right pi. All right, so hopefully maybe the sign is, or sorry, the range is a little bit easier. Because again, if we're going to look at the range, let's look at the range of y equals the sign, or negative sign of pi minus x. Let's look at that function. The parent graph of sine looks like this, 1 to negative 1. You guys agree with me that the range of sine is negative 1 to 1. No stretching, or no vertical stretch or compression, no shifting up or down. Yes, even when you're falling asleep, you can see that this graph is not moving up or down. It is being shifted to the right. But again, if you take the range and you move it to the right or the left, that doesn't impact the actual range, though, right? So we're only concerned right now with this. But then there's also this outside reflection. But again, negative 1 to 1, flip the graph, you're still at negative 1 to 1. Right? Even if you want to stand up and do some jumping jacks, it's still negative 1 to 1. So again, like, well, then what is the range of the cosecant graph? That's what we want to figure out, is what is this range? So if sine is from negative 1 to 1, that means cosecant is going to be from negative infinity to negative 1 and from 1 to infinity, right? Negative infinity to negative 1, they share that point. And then 1 to infinity. Obviously, that's not the graph, because that, I didn't apply any transformations. That's the parent graph. But again, that's understanding that relationship between sine and cosecant. So therefore, I can say that this is just going to be negative infinity to negative 1, included union 1 to infinity. Now, the vertical asymptote is my favorite. Because again, just like we did before, if I have a vertical asymptote at pi, but then I shift my graph, or if I do stretch or compress, or if I shift my graph left or right, that's going to move the asymptotes. Agreed? So if I have x equals, so again, my asymptote equation of my original is x equals pi n. So again, all you need to do for your vertical asymptote is set whatever's inside your function equal to your asymptote equation. So in this case, it's pi n. In our last example, it was pi halves plus pi n. And now we just solve for x. Subtract pi. Can't subtract. Can you do x? Can you do 2 minus 2x? No, they're not like terms, right? This is x. This is pi and pi n, right? So you can't subtract pi from pi n. Yes, nobody says 2x minus 2 is x. Agreed? Pi is a number. We just have a symbol for it. So therefore, I have negative x equals pi n minus pi divided by negative 1. X equals negative pi n plus pi. So therefore, x equals pi n. Anybody follow my logic? Anybody do not follow my logic? Yeah? Huh? Confused from here to here? Yeah, good. Should be. So this is kind of the mental jump that we need to start taking, all right? And the reason why I'm bringing this up is for this chapter, guys, for this chapter, this is an introductory chapter. For this chapter, if you want to leave your answer like this, that's fine. I'm not going to ask for a more simplified answer. That's fine. However, next chapter, this will be the answer you will need to be looking for, OK? So now how do we go from here to here? Well, again, let's think about this as far as transformations. The asymptote occurs at pi. What is my transformation? Shifting it over pi. Does that really change the asymptotes? If I have an asymptote every pi, and all I did was shift the asymptotes over pi, that's not going to change the asymptotes. Wouldn't you agree? Right? That doesn't move the asymptotes at all. So that's why that kind of makes sense. But let me give you another number. So or another way to think about it. So another way to think about it is all even numbers can be represented by 2n, where n represents an integer. Or all even integers can be represented by 2n. Right? 2 times any number, n, is going to give you an even number. Agreed? Another way you could say that is all even numbers could also be written as 2 plus 2n. But do we really need to say the 2 first? No, we just say 2n, right? Or we could also say all even numbers can be rewritten as -4 plus 2n. And wouldn't -4 plus 2n produce all even numbers for any number of n? Any integer of n? Yes. But again, we don't need the -4 or the 2. And again, look at this. All these asymptotes occur at negative pi n. Do we really need the negative? Isn't negative pi n and positive pi n going to produce all the same values anyways? Because n is an integer. N could be positive or negative. So negative pi n and positive pi n are the same. So then why don't we just stick with the positive, because that's considered more simplified than the negative. And then do we really need to start at pi? Do we need to start at 2 to say all even numbers, or could we just say 2n? Right? Because n could be 0, n could be 1, n could be 2. All I'm saying, do you guys see how that's kind of a little redundant to add the pi there? You don't need the pi. Right? We just need the pi n. So again, as long as you understand to take the equation, or what's inside the function, set it equal to the asymptote equation, and you can solve, that's fine. As we get more and more practice, you guys will get better at this, and then hopefully that will transcend into next chapter. Okay? So it's not something you guys need to focus on. That is one of the harder components of today, is that understanding